Hello everyone. I'm Sakshay, and today I'll be talking about integrating custom simulators with ROS. So, a little bit about me. I'm Sakshay. I'm a software engineer at MathWorks, and there I work with the UAV and robotic system toolbox. We develop applications that help other robotics developers develop their own robot applications. So starting with the talk, there are a lot of simulators in robotics. We have been seeing a lot of talks regarding simulators like MATLAB simulations, Omniverse, Gazebo, Carla, Unreal Engine. So simulations form a very important part in robotics, as we first test our algorithms or models in simulations and then we deploy them in real world. But what all these simulations have in common is that they are all connected to ROS. But what benefit does it give them? Why are almost all these simulations connected with ROS? So being connected with ROS, there are three major benefits you can see. First is the distributed computing. You can, because of the structure of ROS, it's a network of nodes. We can run the algorithms in a distributed manner. The vision is working in one node, the navigation is working in another, and so on. Another benefit is that we have access to various tools like RViz, RQT graph, which were discussed in the first talk we had yesterday. And there is a ecosystem of algorithms that are pre-written for us, like localization, move it, and nav2, all these things. So these are the benefits that ROS provides us. So coming on to the next topic, how are these simulators actually connected to ROS? So in this slide, you can see that there are two particular components that operate when we run a simulation. First is the simulation engine and the second is the ROS engine. Both these are independent processes. Now, for them to work together, there needs to be some data communication that needs to take place. For example, let's say laser data. In order for us to publish that to the scan topic, which we have in ROS, we need to get it from the simulation, then we can publish it in ROS. Similarly, the command velocities, these come through the ROS engine CMD-well topic, and these need to be sent to the simulation engine. So how does the communication between two of these processes take place? That is through inter-process communication. So it's a general computer science term. So how inter-process communication takes place is basically there are two methods. First is the shared memory one, and the other is message passing. I'll just go over them in detail a little bit. First, the shared memory. So shared memory, you can think of it like Google Drive. So one person uploads a file into the drive and the other person can access it. So over here, simulation engine and ROS engine both are acting as users of Google Drive, which is the shared memory. Just to go over the process is first we have to allocate a shared memory. We have to create a link, then we acquire a lock, write to the memory and release the lock. A lock is basically, as the name suggests, locking the access to the memory that we have. You may have observed when we are using, let's say, Google Docs, if two people are writing together, it creates a mess. Lock is useful for that purpose so that a mess is not created and memory is not corrupted when we are reading and writing. Similar procedure goes for reading as well. Then message passing is a simpler one. It's simply like WhatsApp. We are sending messages through to two users and they are just communicating with each other. Now, these are the two methods, but what steps you can say we have to follow for what steps are there that should enable communication between the simulation and the ROS engine? We can categorize them into three steps. First is identify the data that we need to share. Then we need to identify the method for sharing the data and then creating the ROS nodes. Let's go over them through an example. So let's say we have a very simple simulator over here. You can see it's a 2D based robot which has laser sensors in front of it, and there is an obstacle in the middle of the simulation. Quickly going over the directory structure of the simulator, you can see that there are two major components that make this simulation. One is the physics engine and the other is the visual engine. So physics engine is a simple one. It is stepping through the physics through the a small timestamp, let's say 0.01 seconds, doing the collision detection and then doing the collision resolution. So this three-step process is a very common one we see in physics engine, this simple one. And for the visual engine, there is a loop that is running at some particular frames per second, and it's displaying whatever we are seeing in the simulation. Both of these physics engine and visual engine run parallelly to show the simulation that we have. And the main driving force behind the simulation is a Python module called Pygame. It helps us to write the physics engine and the visual engine that we see. So just a brief how these three steps we are applying to the simulator we saw. First, we have to identify the data for sharing. Now, there are majorly two data we need to share. First is the robot velocities and the other is the sensor values. So we need to identify in the code for the simulation where this robot object is and where is the sensor object. So we can retrieve the data from the simulation and send it to the ROS engine. Next, for the method for sharing the data, for this particular example, we are going to use MATLAB Python co-execution. I will just get to it when we get in the details. And using Python, MATLAB Python co-execution, we extract the Python objects that are there in the simulation and send it to ROS engine. And the last step is to create the ROS nodes. Since we are using MATLAB Python co-execution, we are using MATLAB ROS2 API to create the ROS nodes as well. So this is very specific to this example. I'll also go over what other techniques you can use if you're not using this same technology that we have over here. First, identifying the data for sharing. So the application runs through a main.py file. And over here, we can identify the two components that we talked about, the robot and the sensor. Now, this first step, it takes a little bit of going through the code and familiarizing yourself with the code to understand where all the objects are coming. So we identified the robot and the sensor. Moving on to the next step, which is identifying the method for sharing the data. We are using MATLAB Python co-execution. What this simply means is we can run Python files directly in MATLAB. All the .py files of Python that we have, we can directly just run them in MATLAB. What benefit it provides, I'll just go over it also. So in this code that you can see, first we have the Python path, which is the virtual environment of Python. So for all the libraries we have installed for Python, we can select that and run Python based on that. And the first two lines are doing that. So the third line is the one actually running the .py file, which is main thread.py. Additionally, it is extracting the robot and the sensor objects which we identified in the previous step. Now, once we have these robot and sensor objects, we can use them to create ROS nodes. This step is essentially getting the objects from the simulation engine to the ROS engine. For creating the ROS nodes, I'll just quickly go over it. It's mostly code. First, we initialize a robot node class. There are various properties you can see, robot node and everything. We are initializing the ROS node, robot node, and we are also initializing the subscriber, the CMD well, which will be used to get the velocity. Next, we have the scan topic, which will be used to send the scan messages. same is the code for that. All these steps are complete. Now let's run the simulation and see how it's working. We run the main thread. So to note here, we are not running this from the typical Python terminal. It is running in MATLAB. The Python code is running in MATLAB. We run main thread and we can see the simulation is running. And we do a ROS topic list and we can see both the topics which we earlier created. These are displayed CMD well and scan. Now CMD well and scan are created. Let's move on to the application of it, which is a simple wall following algorithm. We want to get the scan data, apply some logic on it, and give some velocity commands to the robot. So once we do that, we can see the simulation, the robot is moving according to the velocity commands that we gave. Okay. Right. This overall, we can see how these 3 steps apply to run, to integrate a simulator with a ROS engine. So let's expand this to other technologies. Let's say we want to integrate Unity with ROS. For popular simulators like Unity and Unreal, there are APIs that are available which we can directly use, which help us get the game objects from those kinds of simulators. For simulators like Gazebo, once again, there are APIs which we can use to get the model objects. And we can use these data for sharing all the information that we have from simulator to ROS. Second is the method, identifying the method for sharing data. So there are a lot of inter-process communication libraries that help us with this task. We can use this to create shared memory objects. We can use this to create pipes that help us communicate between 2 processes. We can use communication protocols like TCP, IP, all these to communicate the data. And MATLAB example that we saw, that is also one thing. Next, for creating the ROS nodes, we can use Python, C++, and MATLAB. So yeah. Further on, you can do further development. Let's say you want to visualize the ROS bag. You can use ROS toolbox from MATLAB, RViz from the ROS that is available to us, and Plot Juggler. That is another tool we can use. For SLAM, we can make use of navigation toolbox or SLAM toolbox from the ROS. And for navigation path planning, we can use again navigation toolbox nav to move it. Once we have created all these topics, we can easily use all these tools to create a robot application. So to summarize, we first looked at the simulators that are used in ROS, how these simulators are connected to ROS, the 2 processes that communicate with each other, the steps for integrating the simulation and ROS engine. We saw how it works on a basic simulator and how further development can be done once all these topics are published. So yes, thank you. Any questions, comments?
We'll have to do this really quick, yeah?
Yeah, hi. It was a great presentation, but when we have a lot of other open source libraries which can do simulation for us, I mean, it makes sense to leverage the MATLAB's toolbox, but how far do you think, like what kind of other advanced simulations have you done, maybe with multi-robots or, maybe like 3D visualizations? Do you think, will it be easier to scale this approach rather than just pure MATLAB or just non-MATLAB methods?
It depends. So big simulators, let's say Omniverse that we discussed, those are already integrated with ROS. This technique that I showed, you can use it to connect any simulator with ROS. Let's say you have a very specific application of a gripper. You want to simulate a gripper. Now, simulators usually, they are not very confined to that workflow. You want to model, let's say, very accurate gripper physics. For that, you may need to develop your own simulator. Now that simulator, you can use this technique to integrate it with ROS. So the thing that I showed is a technique you can use to integrate any simulator with ROS.